Today we are learning the Rational Zero Theorem. This is also referred to as the Rational Root Theorem, and I might call it the Rat Root Theorem occasionally. So what it says is, let f of x equal some polynomial, and in this polynomial they labeled a sub 0, which is sometimes referred to as a naught, is the way you could say that, a sub 1, a sub n minus 1, all the way to the a sub n. So a sub n is my constant term and would be the y-intercept in this polynomial. A sub 0 would be the leading coefficient. All right, so all of these a values are the coefficients. All right, and then I have exponents, x to the n minus 1, all the way down to a constant term. Right. So let this represent a polynomial with integral coefficients. All right. Does anyone know what integral means? Integer? Does anyone know what an integer is?
Isn't it a number? Like it's a certain kind of number.
Yeah. It's a certain kind of number, a number in which it's essentially the counting numbers, including 0, but then also all of the negatives of them. So no fractions or decimals. And it says if p over q is a rational number in simplest form, all right, so p over q is some fraction, and is a 0 of the polynomial, it turns out that the numerator is a factor of my constant, and that the denominator is a factor of the leading coefficient. So it turns out that all rational, all right, any number that can be written as a fraction, which includes the integers, all rational factors, all rational zeros of our polynomial are going to be a ratio of the factors of my constant over the factors of my leading coefficient, is what that says. So this is going to allow us to narrow down our search when trying to find zeros, where instead of trying to find them out of everything, we're going to get a finite list, at least for the rational ones, okay? So it is possible to get it to cross at the square root of 2 on the x-axis. That would be an irrational number, all right? But for all of the rational ones, we know which ones we should at least look at. Now the corollary to this theorem, the integral zero theorem, I kind of find to be a little bit weak and almost not necessary. In the case of the fundamental theorem of algebra, the corollary was the really, really strong one. And in this case, it's kind of like, corollary's like, yeah, if the leading coefficient's 1, then it's just a factor of that one. It's like, yeah, we already kind of knew that. Thanks, corollary, right? It's like, It's like if you were writing a really long term paper and someone came along and said you should put your name on the top. And it's like, I was going to do that, obviously. Come on. I'm not going to give you credit for writing this term paper. I did all the work. You just added one little piece. And of course I was going to do that. Right? So the corollary is kind of redundant, unnecessary in some ways. So let's do an example of one of these and see if we can find all of the zeros. Let's see. Well, actually, before we even do that, let's just apply this first of all. So list all rational zeros. All possible rational zeros, I guess, would make more sense. If you can fit possible in there, I'm sorry. Possible rational zeros. Okay? So let's say I've got the polynomial p of x equals, and let's say I've got 2x to the third minus 5x squared plus, I don't know, 6x, and we'll do minus, let's do 10 maybe. All right? So it turns out that my p values are the factors of the 10. So what are the factors of 10? That would be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Right, those are all of the factors of 10. Technically negative 10 in this case. But even if that was positive 10, negative 1 times a negative 10 would still equal positive. So that's why I have to consider all plus or minus combinations of those. And then my q's are going to be the possible factors of the leading coefficient. So those are going to be plus or minus 1 and plus or minus 2. So my possible rational zeros, basically, if there are rational zeros, it has to be from this list. My p's over q's, all right? I don't know why they call them p's and q's, and I don't know why they alphabetically chose to make this the p and that the q. Like, I don't know. It seems like this one should have gone first alphabetically, but whatever. It's just going to be all combinations of the p's over the q's. All right. So let's consider the denominator of 1 first. So I could have plus or minus 1 over 1, which is 1. I could have plus or minus 2 over 1, which is 2. I could have plus or minus 5 over 1, which is 5. I could have plus or minus 10 over 1, which is 10. All right? So I just put all of these over this denominator. And now I've got to put them all over the 2 denominator. All right? So I'm just making a list of all possible combos, really. So let's see. Those ones would be 1 over 2, so plus or minus a half. 2 over 2, which is what? 1, and I already got that one, so I don't need to write the 2 over 2 again. Plus or minus 5 over 2, right? I mix those two together. And then I got plus or minus 10 over 2, which is 5. That's all right. I know you got it. And we already have 5. It's all right. It's all right. So yeah, it turns out if I was looking for zeros and doing like my little synthetic substitution chart and trying to like figure all that out, these would be the numbers I would try. All right, and then I could even in a more powerful way end up mixing and matching them to figure out I could use Descartes' rule of signs to figure out how many positives and how many negatives I would expect. Actually, let's do a part B to this problem. Let's find them. Yeah, so I'll call that part A. So let's find all zeros. So the zeros in this problem are not necessarily rational, but it's a really good place to check. A lot of polynomials are, or at least polynomials within a math textbook, a lot of them will have some sort of factorable answers. Sure. So let's just do a Descartes' rule of signs analysis so we can narrow our search down a little bit. So how many sign changes are there for the positives?
3.
Okay. So yeah, 1, 2, and then back. So yeah, 3. And then let's figure out what p of negative x is. So let's see. So that would have been negative 2x cubed, negative 5x squared, negative 6x, and negative 10. So how many sign changes are here? 0. How many total zeros am I expecting? 3. So it could be 3, 0, 0, right? Oh, and I'm clicking on stuff. What's the other possibility? 1, 0, 2. So based off of these results, I think we just cut our search in half. I mean, well, first of all, if I knew I was looking for rational zeros, by using this root theorem, I had cut down my list from infinitely many numbers down to like a list of how many is there? That's what, 5, 6 times 2, 12, right? So I narrowed it down to 12. That's pretty good, going from infinity to 12. And now looking at this, I know that there's no negative zeros, ever. So I can eliminate all of these negative possibilities, so I just cut my list down to 6 numbers to try. So it's like, I'm really on a roll here. And then once I start trying one, I'll probably find one positive one or something like that. But once I find 2 positive ones, what would that tell me? Like if I found 2 positive zeros, what would I know about my remaining 0? That it would also have to be positive, because I know it's either 1 or 3, right? But if I end up trying all of them and I find only 1 positive, what would I know about the other zeros? I would know that they had to be imaginary. All right, so see how like this sort of analysis would help us really narrow down our search? Because 2 days ago we had some students that were, I don't think they were frustrated, but we're just saying like, how do I know which ones to try? And that's exactly a legitimate question, right? That's exactly what we should have been wondering. So let's see. Let me. So 2, -5, 6, -10. So 2, -5, 6, -10. So let's do some synthetic substitution, and this time, my column over here are going to be all the p's over q's, and in this case, the positive p's over q's. All right, so now I just made this problem up off the top of my head, so no guarantees how pretty it's going to be. But based off of our list, I'm guessing students would probably want to start with the integer ones, the 1, 2, 5, and 10, and they'd probably want to leave the fractions to last. So let's start with 1, I guess. 1 is a pretty good place to start. So we'll try 1. Bring down 2. 1 times 2 is 2, with a -5 is -3. And then 1 times -3 is -3, with a 6 is a +3. 1 times 3 is +3, with a -10 is a -7. So that didn't work. So I guess we could try 2 next, because 2 was on our list. And notice I'm only trying the positive ones, because that's what Descartes told me to do. So bring down the 2. 2 times 2 is 4, that's -1. 2 times -1 is -2, with 6 is 4. And then 2 times 4 is 8, with -10 is -2. So based off of this, what do you think that 1/2 is going to be one of my roots? Based off of looking at those.
Yeah.
Why? What do we think? Because between 1/2 is going to be between these two. Does it look like it crossed the x-axis between those two? No. It could have. If it was one of these situations where it came up and just like ricocheted off of it, it could have, but I'm going to guess for now, let's ignore a half and we'll just keep going. But it does appear that this is getting closer to 0, right? From -7 to -2, I'm approaching that x-axis. So let's try 5. So let's see, 5 and 2 is 10. With a -5 is +5. I don't think this one's going to work either. I don't think. We'll see. Yeah, oh no, this one's not going to work. 31. Yikes. And then 5 times 31. 155, so 145. No. So what does this tell us based off of your analysis? Yeah, it crossed the x-axis between 2 and 5. So what's a number that you'd want to try in our list? 5/2 is probably a good guess. All right? I'm thinking it might be. And even though we don't want to, our kind of detective work has led us there. And yeah, so now I'm going to try to do some fraction work in our heads a little bit. We'll see how well this works out for us. So let's see, I bring down the 2. So 5/2 times 2 is just 5, with -5 is 0, right? 5/2 times 0 is 0, bring down the 6. Man, this one's not going to work either. Interesting. 5 halves times 6, half of 6 is 3, times 5 is 15, with a negative 10 is positive 5. 5 halves, by the way, is 2.5. Right. So between 2 and 2.5, it goes from negative 2 to positive 5. What does that tell us? Yeah, somewhere between 2 and 2.5, it crosses the x-axis. The bad news for us is we don't have any numbers between 2 and 2.5. So that means I am expecting... I know that there is a 0, but it must be irrational. So sadly, it doesn't help us too much. So we are going to just have to keep searching, and we'll be looking for other ones. So this is kind of bad news so far. But at least I know roughly where it is, right? So let's try some other numbers. We've got, what, 10 to try? The number 10? We still haven't tried? And we still haven't tried a half. So let's try 10. So bring down the 2. 10 times 2 is 20. With a negative 5 is 15. 10 times 15. Oh man, this is getting so far off. Nope. 150 plus 6. 161. No, 156. What am I saying? And then 10 times 156 is 1,560. Minus 10, 1,550. Ugh. So yeah, that appears to be going off towards infinity as I plug in more positive ones, which I would have expected because the original polynomial is an odd degree with a positive leading coefficient, so I know that as I go further to the right, it is going to head further off to infinity. Let's see, so the only one I have left to try is a half. And I'm hoping my example is a little bit more helpful than this, but who knows. We'll see what happens. So let's see. Bring down the 2. Half of 2 is 1. Negative 5 is negative 4. Half of that is negative 2. Yeah, this doesn't look like it's going to work either. So what's that? Wait. 4, and then half of 4 is 2 with negative 10 is negative 8. For shame. Well, but this did still give us some information. Now, unless it somehow had, like between some of these points, unless it had like some really close together irrational zeros, I'm thinking that it's probably the situation where it's probably an irrational and 2 imaginary is likely the case. Unless somehow there was 2 more irrational zeros hiding between some of our numbers. Which could happen. It could happen. Let me actually start up Sketchpad here just to graphically see what's going on. I think it's starting up. So unfortunately, we, in our current abilities, we've narrowed down our search as far as we could, but this problem would not be solvable to us using our current techniques because we don't know how to solve a cubic function. We know that it's likely got 2 imaginary solutions, and we don't know how to find those. So yeah, and it wasn't any of the rational ones. Let me open up this and let's see, pull up a new little window, and let's graph this and just see what's going on. So at least we can get some conclusive results from this. So 2x to the third minus 5x squared plus 6x minus 10. And so yeah, you can see that it did only have the 1 positive, which is what we'd suspected. and that one positive is likely irrational. I think I can actually find out what that is for us if I snap that point right there, and I go to measure coordinates, and apparently it's around 2.18 rounded. So yeah, so I'm sorry we didn't have a better way to do this, or I didn't have a better problem. We'll do one that works out next. Whoa, that's weird. I'm like clicking with that mouse and working with the other one. So so I'd get x equals 2.18 is the only real one. And then if I wanted, I could do I could say that g of x or something is x minus 2.18. And if I divide my original polynomial by that factor, I could then get a quadratic that would give me my two imaginary. But we wouldn't go this far with this problem because it was irrational. We wouldn't have been able to go any further. So, sorry. Let me find a problem that's going to be a little bit friendlier to us. Where's one with some like good old classic? Yeah, this is a good one. I like it a lot. Well, actually, I need one that works out. We just had one with imaginary. Let's do a quick example. Let's see. Let's do. I like this one. Let's do p of x equals x cubed minus 5x squared minus. Oh man, I'm writing on a slope. 5x squared minus 22x plus 56. This is going to be some ugly math for us, but that's okay. So let's see. So my q's are plus or minus 1. My p's are plus or minus 1. And bless you. Let's see. Then we'd have. I might write these in pairs, actually. I like this better. 1 goes into it 56 times. 2 goes into it, let's see, 25 plus 3, 28 times, I believe. 3 does not go into it. 4 goes into it. 4 goes into 28 7 times. 7 times 2 is 14. 5, no. 6, no, because 3 didn't. 7 does. 7 goes into 14 twice, and 2 times 4 is 8. So here's my list of possible factors. Now technically the integral zero theorem applied because of this being 1. I know that my factors are just one of these. Okay, my possible rational zeros. According to Descartes, I'm expecting, let's see, as many as 2 positives. And I'm guessing probably 1 negative here, but so it's going to be 2 or 0 for the positive. I'm expecting 3 total, right? And if I do p of negative x real quick, I will get negative x cubed minus 5x squared plus 22x plus 56. So yeah, there's 1 sign change there. So 2, 1, 0 or 0, 1, 2 are the possibilities for this. So unfortunately in this case I can't eliminate all of the positives or all of the negatives because I do know for sure that there's at least 1 negative. So I guess that's where we get to choose our quest. Do we choose to search in the negatives since we know there is 1 that's negative, or do we choose to search in the positive because there's possibly twice as many of them that we'd find 1, but there's also possibly none of the positives that would work. So that's kind of our interesting situation here. Let's see, I'm going to grab a snapshot of this and move to the top right over here, just so I'll have room for my table. And so I can just see whatever's going on. So let's do this. So I've got synthetic substitution. I've got 1, negative 5, negative 22 is going to be fun to multiply stuff by, and 56. And so let's do this. So we're going to try all p's over q. So what do you guys want to try first from my list? You want to look for positives or negatives? You could flip a coin, it wouldn't matter. Positives, yeah. I guess that'll avoid more sign errors, potentially. And I guess we might as well start with the small numbers, right? So we'll start with 1. So bring down the 1. 1 times 1 is 1, and negative 4. Negative 4 is negative 26. Negative 26 and 56 is positive 30. So currently, I'm up above the x-axis, right? So I'm starting to think, hopefully I'll start coming down towards it, is what we'll be hoping. So let's try 2 next. Not because 2 is the next number, but because 2 is the next number in this list, right? So for instance, I'm not going to try 3, right? So let's see, 2, 1, negative 3, negative 6, and that is negative 28. Ooh. I think it works. We found one. Haha. Victory. Yay. All right. Now, so now we actually can solve this problem a lot easier now. I've got a depressed polynomial I could work with, which we could actually try to factor. I think it is factorable. So let's work with the depressed. In this case, yes, we could, since it's a quadratic, we could solve x squared minus 3x minus 28 and set it equal to 0. But just for the table practice, let's keep using the table. I believe this is all factorable. Yeah, it is. So let's see. So I just tried 2. Let's try 4 now. So 1 and 4, negative 1, negative 4, and that is negative 26. 4 and negative 26 is going to be like negative 104 with 56, negative 54, negative 48, is it? So notice that, so we started up above the x-axis, we hit the x-axis, and now we're down below it. So hopefully, in a little bit, we'll start coming back up. So let's try 7. Let's see, so 1 times 7 is negative 2, negative 14, and negative 22 add to be negative 36. And that's going to be 2 negative, right? 7 times 6, 42. Did I do? Oh.
It's positive 2.
Thank you. Thank you. Thank you. You guys got my back. Yeah, because 7 and negative 5 is positive 2. Good call. Good call. 7 times 2 is 14, which with negative 22 would give me 6, 8. And 7 times 8 is 56.
It'd be negative 8.
It'd be negative 8. Aha, even better. Thank you. Man, you guys got my back. Right? Now, question. Should I try 8 next? Positive 8?
No.
Why?
Because you have both your positive numbers.
Right, because I just found 2 positive zeros, so I know I'm in this situation here, right? And I don't want to waste I know there's no more positive roots. So I know there's just 1 negative 1 left over, and I also know that there's no imaginary ones left over. All right? Now, like I said, once again, I could actually work with a depressed polynomial and just find it real quick, but let's just get some table work here, because I think the analysis of the chart is going to help us later on. So I guess we could try like negative 1. I don't know. So 1, negative 1, negative 6, positive 6. That would be negative 16.
Yeah.
And then positive 16 and 56 is 82. So that's too high. We'll try negative 2. So let's see, negative 2, negative 5 is negative 7. 7s are good in this one, I think. 14 and negative 22, right, is negative 8, and 16 and that. Wait a minute. Is that also 82? No, wait a minute. Are those 82 or 72s? What did I have here earlier? 16 And 56 would have been 66. Those are 72s, guys. Oh, shame on me. At least I caught that one. Well, either way, it didn't matter for the sake of this problem because we're only interested if it's equal to 0. So yeah, this is 72 and 72. Now, I'm expecting, now notice that these are equal. That is no direction change between two of those, which means there's probably a minimum or a maximum that occurred between those. I just want to point that out, if we were trying to find those. Let's see, let's try -4. I've got a good feeling about this one. Show me the numbers here. So let's see, -4 and -5 is -9. Oop, now I'm not so sure, I'm scared of it. That's +36 with -22, so that would be 14. Ooh, I think I like it. Right, 4 and 14 I had earlier as multiplied to be 56. This is -56, and we found it. We found it, ladies and gentlemen. We found all three of our zeros. So I just want to point out that with Descartes, with the rational root theorem, with the fundamental theorem of algebra, I know how many zeros I'm looking for. I know what their signs are going to be, or possibly going to be, and I also have a list of what the rational ones would be. All right. So between all three of these, we're really like narrowing down our search and doing detective work to figure out what's going on. All right. Now, one of the trickier things that can happen, remember when we have a graph that like ricochets off like that? What that function looks like? We'd end up having the factor x minus 2 twice. So x minus 2 squared could show up. One of the things that can be tricky is if the same zero shows up twice. Sometimes we wouldn't have anticipated. It would have thrown us off on this, right? Because what if I did all of my, what if I tried all of my positives and then like I didn't find another one? It's possible like I would have to try 2 a second time. So that can be a little bit sneaky, a little bit tricky. So just be careful. But like I said, we could have worked smarter technically and used depressed polynomials to make things a little bit easier. But yeah, so that's the idea behind this. Narrows down our search, find our zeros quicker. Well done, ladies and gentlemen. Have a great day.